This is Duke University.
So what I'm going to talk about is a new way to reliably estimate the regional solar panel capacity. I don't know why I can never say that. This is actually pretty interesting because I would have never guessed that the US government or any government had no idea where solar panels were deployed. I would have never guessed that. But they don't, and so it came up in a completely different discussion from our energy disaggregation about the fact that is there a way that we can find a way to actually be able to estimate where solar panels are deployed in the US or elsewhere. So these are the people, among others, that have been working on the project. So as I said, there's an interest in trying to figure out where the solar power capacity is available in the US. And right now, the only way there's really good estimates of that, and good should be in quotes, is basically audits or questionnaires. And I don't know about you all, but I get a questionnaire in the mail, and I just sort of throw it. You know, it's like, I don't have time for that. So the thing is that because of that, really nobody is able to estimate what the solar capacity is. So Kyle, knowing that we were interested in image processing of all sorts and big data, we thought to ourselves, well, you know what? There's color satellite imagery available, also hyperspectral, but we haven't gone into that yet. So there's all of this imagery, and the question is could you use computer vision to go into this imagery and figure out is there or is there not a solar panel? And so we sat down and spent about, I don't know, a month or so and said, can we just do something really quick to see if there's a way that you could do that, use this sort of imagery and get a decent estimate of where the solar panels are? So we got this imagery. What we did I skip one? No. We got this imagery, and we basically just cut out a whole bunch of these little image patches, 50 that had solar panels in them, 50 that did not have solar panels in them. And we basically came up with a real simple computer vision algorithm to automatically locate the solar panels in these little image chips. And what we found was using fairly simple techniques, we definitely want to build on this, is that we were able to take those set of 100 images, and 92% of the panels were found using these automatic techniques. So we're not having humans in the loop. We're doing this all automatically. In those 100 images, we were able to detect 92% of the panels, and we only had 4 false alarms. So we were able to look at those images with a computer vision technique and say, solar panel yes or solar panel no. And so the thought is that given that there's a whole lot of imagery out there, that we can take these techniques, build on what we've sort of done in a preliminary way, and be able to help the people that are interested in knowing, is there a solar panel here? How much capacity does it have? And be able to do that relatively accurately. So we're not suddenly saying that my house, which has no solar panels, has a solar panel. And one of the things that you saw on the first slide, if you read all the way to the bottom, is that there's actually a Data Plus set of students that's going to work on this over the summer and hopefully build on it and make it better than what we did in the month or two that we tried it. But just giving you sort of a sense of what these images look like, this is a set of these image chips. The red regions show you where there are solar panels. The green regions, you can see one right here, indicate where the algorithm said that there was a solar panel. And in these particular set of images, all but one solar panel was detected. So that one on the top left, which you see has got a little bit of a different shape than sort of typical solar panels, our initial algorithm detected that. And these images, again, little image chips, basically of rooftops, do not contain any panels. And there was only one place down here where actually we picked up sort of a piece of the road. We're not even picking up something that's on the top of the roof. Said that there was a solar panel when there wasn't. So our goal is going forward to focus on algorithms for reliable large-scale estimation of these solar panel capacities and output by regions, so that hopefully someday we'll be able to take a state, map it out, and say, this is where you've got plenty of solar panels, this is where you don't. That's all I had.
Great. Thanks so much. And I knew I wouldn't be able to compete with Kyle's slides, so that's all I have. So my job is to talk to you about utility data and actually convince you that utilities are an exciting thing to work on. And I know, like, if you're like me, the only attention you actually pay to utilities is really none. You get your bill and then you ignore it. So, you know, why is utility data actually interesting? Well, as Kyle mentioned in the beginning, probably the most amazing transformation in the electricity sector is the deployment of the smart grid. Right? So now I was trying to find the latest statistics. We have over 50 million smart meter installations already. Those installations are generating data at an amazing rate. So from a social science perspective, what's happening here that's really interesting, you can think about every utility that moves into the smart grid area essentially becomes another experiment. Each utility is a giant social experiment. And I think overall, the smart grid, in a way, is actually the largest social science experiment that we've ever sort of been part of. So what is happening here from a research perspective, we have the ability for the first time to really understand how people actually make choices and how people consume energy on a vast scale at very, very, very high frequencies. So that enables us to sort of build models of consumption and really understand what is happening. So from an economics perspective, you know, if there's one bit of economics you may remember, maybe you don't, economists really care about sort of marginal costs. So prices have to equal marginal costs. Now, in the electricity space, that is not true because you have a wholesale market where prices fluctuate a lot, and then you have your retail market, what you get at the end, you know, what you get in the mail, where your prices are going to be pretty much fixed. So there's this huge imbalance between what happens in the wholesale market, where the actual costs are being reflected, in the retail market where they're not. So this technology that we have actually gives us the ability, at least in principle, to actually connect these things, right? So imagine a world where you as a consumer would actually pay the cost of electricity, so your prices may potentially fluctuate in real time. So that's a world in which, towards, I think we're slowly progressing. So we're seeing more and more movement towards sort of real-time pricing, and that becomes interesting because it opens up the question of how we as individuals are going to be able to actually respond to these conditions that may potentially change in real time. So 1984, a very important year. The movie Terminator appeared. A couple of years later, there was a professor at Harvard Business School called Zuboff, and she wrote a very interesting book called The Age of the Smart Machines. So I don't know if it was inspired by Terminator or not. But basically what she introduced at that point was this terminology of, you know, is it better to informate or to automate, right? If we want people to respond to new things and new challenges, what should we do? Should we provide them with information and then ask them to sort of figure out how to do things? Or should we sort of automate their behavior through technology? So one of the things that we have available to us through the smart grid, we have the ability to connect technology, whether it's sort of smart displays, thermostats, all of these things. They can all be connected to each other and to the grid through smart meters. And then the question becomes, what's the right way to actually do this? So, you know, my work is basically involves working with utilities in designing, implementing, and evaluating various sorts of experiments on a large scale in the population to figure out what's the best way for people to experience and respond to prices and to energy. So what are we learning from this? Well, we're learning that information doesn't do very much. If I just tell you that the prices are going to go up, by and large, you're not going to respond very much, so you're going to need some technology to help you along to actually make better decisions. Very passive technology also doesn't do very much. Even if I put a display in your home that's going to tell you, you know, today at 2 p.m., like the electricity price is going to go up tenfold. Some people are going to respond. Most people are going to get bored looking at the display after a week, and by and large, there won't be much of an effect. What does work, however, very well are technologies that automate your behavior. So Kyle already mentioned smart thermostats. These smart thermostats started by initially just communicating and responding to prices that changed in real time. Now we have smart algorithms built on top of the smart thermostats that learn your behavioral pattern. They also track your occupancy, so we know, what actually happens. So I think this is a very exciting area. So I think utilities are worth taking another look at from a sort of research perspective. And as Kyle also mentioned, we're also moving towards sort of Internet of Things type framework, where not only are we getting information on energy consumption, these smart devices themselves have sensors in them. They collect information on behavior and everything that's happening in your home at an increasing pace. And all of that information goes somewhere it's being made available. So I think to the extent that we can use all of this to make people's lives better, it's a worthwhile thing that we can work on. Thank you.
Hi folks, I'm Brian Prest, and I'm going to talk a little bit about the research that I'm working on looking at the effects of shale gas on the natural gas supply elasticity. And as you know, I'm working on this with Richard Newell and Ashley Vissing. So in principle, what we're looking at is how shale has affected natural gas supply elasticities. And the reason we're looking at this is because there's a story in the industry that shale is more price responsive. If prices go up, we should expect to get more natural gas supplied than under conventional drilling. So why is this the case? Well, there's several things. One is that as kind of background, conventional natural gas tends to be a high-risk endeavor. You're going to end up drilling a lot of dry holes to get a small number of highly productive ones. So ultimately, it's about finding that kind of jackpot reservoir, or finding the needle in the haystack. One industry player I talked to, referred to it as big game trophy hunting. By contrast, shale is often referred to as being like a manufacturing process. What does that mean? It means that we can produce more shale gas on demand. If price goes up, we can get it. Why is this the case? It's largely the case because shale gas is much more widely distributed. So we know where it is. The trick is just getting it out of these relatively impermeable reservoirs. And that's a challenge, but it's something that we can do on demand. As a result, shale gas production tends to be more predictable and less variable. And as another feature of it, it tends to have a very different decline path, very different production profile for each well. In particular, you see this high initial production once you drill the well, followed by a steeper decline rate. And all of these things kind of combine together to suggesting that shale gas should have a larger price response than a conventional natural gas. So just to illustrate this last point of the different production profile, you can see here a plot of a couple of wells in our data of unconventional wells. This is kind of your average unconventional well compared to your average conventional well. And you see the conventional well has this huge production right off the bat and declines pretty quickly. So you can imagine if you drill an unconventional well, you're going to get a big burst of gas production right off the bat. So in general, let's take a step back, and I want to just kind of explain the different steps of the process of producing natural gas. So step one is you need to lease and permit a well. Step two is once you have those things in hand, you can actually bring your drill rig out to the site and start drilling. This can take about a month or so. Then, at least for unconventional wells, you frack the well, and then you need to complete it. This can take also about a month or so. The completion process, the fracking is to loosen up the rock to allow the natural gas to flow to the surface, and then the completion is where you case the well to allow a path for the gas to flow to the surface and not leak out. And then finally, once you've done all that, you produce the gas according to that kind of decline path that we saw on the previous slide. So the reason I'm showing you this is that you can imagine that shale gas has kind of fundamentally changed the way natural gas is produced on each of these different margins. The leasing process is different based on who typically owns the gas resources. Drilling is different because drilling tends to involve horizontal drilling for unconventional gas. Fracking is different because you often do not need to frack a conventional well. And then the production paths, as we saw on the previous curve, are different. So what we're trying to look at is how how shale has affected the price responsiveness on these various different margins. So how are we doing this? We have a lot of data, hence this me being on the energy data analytics panel, from a company called Drilling Info. We have information on hundreds of thousands of oil and gas wells. We're focusing in Texas and the Gulf of Mexico. And for each of these wells, we have a lot of information, what kind of direction drilling they used, the reservoir they were trying to tap into, when each of those stages happened, when they were permitted, drilled, completed, and so on. The depth of the wells, location, we have a ton of information, hundreds of covariates. And then for each of these wells that ended up producing, we have their monthly production over time. So what we're doing is we're taking all of this data, matching up with price data to try to see how price responsive shale versus conventional wells are, and try to map that into a total supply elasticity.